Hello everyone, welcome to Sam Science View channel. In today's video, we are going to listen to a science fact. How are gemstones created? So it's a long, brief video. So I have split this into parts. So if you have any science related queries, you can ask it and get it rectified through this channel. And now let's get into the video. Most gems form naturally as minerals within the earth. Most form as crystals, solids whose atoms are arranged in highly ordered repeating patterns called crystal systems. Learning about mineral crystallization and the geological processes involved in gem formation will help gemologists understand some of the properties they will encounter in gemstones. You can make your own crystals by the good way to learn how crystals grow. The simplest method involves crystallizing sugar to make rock candy. Take a pot of water and stir in as much sugar as you can. When you see it settling on the bottom and no more dissolves, you have reached the saturation point. The water has absorbed all the sugar it can. This condition is called supersaturation. Next, bring the pot to boil. At boiling, the saturation level changes. The solution is no longer supersaturated. You can now add considerable more sugar. So, add more sugar until you reach a supersaturation level. Remove the pot from the stove as the water cools to room temperature. The amount of sugar it can hold in suspension will return to the previous level. The excess sugar must come out of the solution. As it does, it will crystallize. Hang a string in the sugar solution for the crystals to grow on. Put a weight at the bottom of the string to keep it straight. Although the process itself isn't fast enough to observe unneeded, you will see changes in the crystals every few minutes. We'll see the basics of mineral crystallization also. This simple exercise actually introduces you to 4 of the 5 requirements for mineral crystallization to occur: ingredients, temperature, pressure, time, and space. Inside the earth, the ingredients of crystals are more complex and numerous than our sugar solution we have seen. Solutions may contain many different minerals. At a high enough temperature, a solution can hold many minerals in suspension. As the temperature drops, the amount of solid ingredients it can hold in suspension drops as well. When that occurs, crystals are formed. In fact, different minerals in the same solution will crystallize at different temperatures. For example, corundum might crystallize first. As the solution continues to cool, topaz might form next, then quartz. You can see to the picture. Pressure has no effect on the formation of rock candy, which we have dated. However, it takes the proper combination of pressure and temperature for minerals to crystallize in the earth crust. The germs that crystallize underground typically require very high pressures and temperature. Time and space are fairly straightforward requirements. The right combination of ingredients, heat, and pressure must last long enough for the minerals to crystallize. They also need room to grow. Obviously, you can't grow a crystal 3 cm long in a cavity only 3 mm long. The underground environment looks like this, which exists underground that make a crystallization and gem formation possible. The earth crust varies from 3 miles around 4.8 km thick under the seabed to 25 miles under continents. Under the crust lies the mantle, approximately 1860 miles thick. The mantle makes up 83% of the Earth's volume. It's composed of molten rock called magma. In the rare occasions where it reaches the surface, we call it lava. The mantle is hottest near the center of the earth, and heat currents keep it in constant motion. The crust and mantle meet in a tumultuous zone with high pressures and temperatures. Several plates make up the crust and float on the liquid mantle. As they run into each other, and some are pushed down while others are raised into mountains. The magma is also in constant motion. Its movement and pressure constantly act on the bottom of the crust, creating wear and fracturing. As a result, rocks break free from the crust and are carried away in the fluid magma. Much of this rock material melts, changing the chemistry of the nearby magma. Some of the smaller particles are destined to be inclusions in future gems. Heavily fractured, the lower surface of the crust contains numerous cavities. Fluids escaping from the magma flow through these fractures and cavities. Here we find the proper condition for crystal growth. Chemical rich fluids supply the necessary ingredients. The cavities offer space to grow. The temperature and pressure here are high. As the fluid moves through the crust, it cools enough for crystallization to occur. The only requirement left is time. So, how interruptions to crystal growth affect germ formation? You might think that in geological terms, time would be more than sufficient for crystal formation. However, in this highly tumultuous environment, passages constantly open and collapse. Often crystals start to form, then the passage feeding the mineral rich fluid to the cavity closes. At this point, all growth stops. If the passage reopens, growth will resume. In most cases, this on and off growth pattern is undetectable in a crystal. However, in some cases, it has noticeable effects. First one is in color zoning. Sometimes the successive layers of growth will have slightly different chemical compositions. When this happens, you may see color zoning in the crystals, as you can see here. And the second one is twinning. Occasionally, the new layers will have different orientations. This causes twinning. So, this is the twinning. And the next is parting. In some crystals with twinning, the new layers don't bond completely with each other. When you see parting on a star ruby, for example, the layers didn't bond. Crystal specimens composed of different minerals. Even if a closed passage reopens and fluid again enters a cavity, a totally different mineral may crystallize over the existing material. Indeed, temperature, pressure, and the chemistry of the fluid solution often vary over time. Different conditions will produce different mineral crystals within a cavity. When opening a deposit, you will commonly see different minerals covering earlier layers. So many minerals cover many layers. So next one is about the inclusions. Such changes of conditions within a cavity is also one cause of gemstone inclusions. A new crystal may start to grow on an older and larger one, only to have its growth process stop. If conditions that allow the original crystal to grow resume, the older crystal will grow over the newer one. Sometimes two different minerals will crystallize at the same time. If one takes off and starts growing faster, it will engulf the other. This is how pyrite crystals end up inside emeralds. In still other conditions, chemical impurities can exist within a crystal. If the temperature or pressure changes, the impurities can crystallize within the host crystal itself. In effect, the host crystal acts as a cavity holding ingredients that just need the right conditions to crystallize themselves. This is how rutile forms inside quartz and corundum, which you can see here. Next is phantoms. In some rare situations, phantom crystals or inclusions may occur. This happens when a new layer of crystals grows over a transparent crystal. For example, a fine layer of feldspar may cover a quartz crystal. Subsequently, conditions change again and the growth of the original transparent crystal resumes. This time, a new layer of quartz covers the feldspar. The resulting gemstone shows the outline of that fine secondary crystal layer as an indistinct form, like a nearly transparent ghost or phantom, hence the name. Next is healing fractures. During the rough and dramatic changes in the crust, many crystals are broken. However, if the conditions for growth are present, material can seep into the fractures and crystallize. In this effect, this heals the fracture by growing the crystal back together. However, these breaks never heal completely. Fine cavities filled with gas remain in the previous gap. We call this type of inclusion a healing fracture. The fine cavities that remain may resemble fingerprints, so geologists also refer to these inclusions as fingerprints. The next one is strain. The tremendous pressures in the underground environment of germ formation compress many crystals beyond their natural size. This strain can also make a stone prone to breakage. Tourmalines, garnets, and even diamonds may have this level of strain. Many fasters have placed these stones on a lab only to have them shatter. The forces inside the stone literally cause it to explode. Now let's see some of the geological processes and gem formation. Gemologists now understand mineral crystallization fairly well. Advances in geology as well as synthetic gem manufacturing have unraveled some of these mysteries of nature. Creating gems in laboratories involves mimicking conditions that exist underground, only vastly reducing the time required. Traditionally, we were taught that there are three kinds of rock formation process. First one is the igneous rocks created with heat deep within the earth. The second one is metamorphic rocks, which are formed when heat and pressure conditions change existing minerals into something new. And the third is sedimentary rocks, which are formed from deposits of sediment. Today, geologists refer to describe rock formation as involving four processes with molten rock and associated fluids, environmental changes, surface water, and germ formation in the Earth's mantle. We have to examine how each of these processes affect germ formation. Our knowledge notwithstanding, mineral and germ formation are neither simple nor straightforward. Minerals and gems are continuously being destroyed and recreated in a rock cycle depicted in this chart. You can see to this how the rock cycle works is through the igneous rocks, which is being sedimented to form sedimentary rocks, and it is metamorphized to metamorphic rocks, and it is melted back to magma. So it is being interrelated and correlated in a cyclic fashion. This is called the rock cycle. Now let's see about the molten rock and associated fluids. Technically, gems rarely form in the Earth's magma itself. Rather, they form from fluids that escape from it, such as gems from hydrothermal deposits and pegmatites. First, we will cover two exceptions to this process: the magma and gas crystallization. First is the magma crystallization. Magma contains a variety of elements as it cools, the elements combine to form minerals. Exactly what mineral varies with available ingredients, temperature, and pressure. Each time one mineral forms, the available ingredients change since some ingredients are pulled into crystals. As magma goes through various stages of changing temperature, pressure, and chemistry, different minerals are being formed. And the aggregates are, however, unless the conditions are just right, crystals won't form. Instead, magma will simply cool into a solid mass of small interlocking crystals, what they call the as aggregate. And the next one is phenocryst, which is in some cases one mineral will crystallize nicely, then before any more crystals can form, the magma will find a break in the crust and rush towards the surface. Here, the pressure and temperature are too low to allow crystallization. Instead, the rest of the magma cools into fine grained rocks with the original crystals distributed throughout the interior. These are called phenocrysts. Corundum, moonstone, garnet, and zircon are often found as phenocrysts. The Chanthaburi and Trat districts in Thailand have large deposits of ruby and sapphire phenocrysts, which we can see here. Next is the diamond crystallization. Diamonds crystallize at temperatures higher than other minerals. Scientists now believe that most diamonds may form in the magma near the Earth's crust, where it is the coolest. If true, this also means that conditions for diamond crystallization are the most common underground. Diamonds may actually be the most plentiful crystals in the earth. They just aren't the easiest to reach. We will discuss diamond in more depth later on. Next is the gas crystallization. Have you ever wondered why some crystals are doubly terminated while most are broken off at the base? Most crystals grow on a solid base of other minerals. However, a few actually grow inside gas bubbles. These gems form after the magma has reached the surface. During a volcanic eruption, rising magma undergoes a rapid reduction in pressure. This causes water bubbles to form, just like removing the cork from a bottle of champagne. Sometimes these bubbles will contain high concentrations of certain elements. If the right combination of temperature and pressure exists for a long enough time, doubly terminated crystals are formed. Some of the best known examples of gas crystallization are so-called Herkimer diamonds. These quartz crystals get the first half of their nickname from their source, Herkimer, New York. For some gem enthusiasts, the water clear clarity and shape of these gems evoke the look of diamonds, hence the second half of their nickname. Of course, quartz gems aren't diamonds. Garnet, topaz, and spinel may also form through gas crystallization. So, this is about the gas crystallization, and it's a long, tedious thing to know about this gemstones. So, this is the part 1 of this how gemstones are being created. We'll meet in the next part 2 of this gemstone formation. We'll meet in the next video with this science fact. Until then, it's goodbye from Sam. Keep in touch with that for the part 2.